Okay, testing, 1, 2, 3. Give me a moment to just make sure that stream is working. Alright. Stream is working, so let's just get straight into it. Chapter 6. Cosets and Lagrange's Theorem. Lagrange's theorem, one of the most important results in finite group theory, states that the order of a subgroup must divide the order of a group. This theorem provides a powerful tool for analyzing finite groups. It gives us an idea of exactly what types of subgroups we might expect a finite group to possess. Central to understanding Lagrange's theorem is the notion of a coset. 6.1. Let G be a group and H a subgroup of G. Define a left coset of H with representative G and G to be the set GH equals GH for H and H. Right cosets can be defined similarly by HG equals HG for H and H. If left and right cosets coincide, or if it is clear from context to which type of coset that we are referring, we will use the word coset without specifying left or right. Example 6.1. Let H be the subgroup of Z6 consisting of the elements 0 and 3. The cosets are 0 plus H equals 3 plus H equals 0, 3. 1 plus H equals 2 plus 4, 2 plus H equals 1, 4, and 2 plus H equals 5 plus H equals 2 and 5. We will always write the cosets of subgroups of Z and Zn with the additive notation we have used for cosets here. In a commutative group, left and right cosets are always identical. Example 6.2. Let H be the subgroup of S3 defined by the permutations 1, 1, 2, 3, and 1, 3, 2. The left cosets of H are 1, H equals 1, 2, 3, H equals 1, 3, 2, H equals 1, 1, 2, 3, 1, 3, 2, and 1, 2, H equals 1, 3, H equals 2, 3, H equals 1, 2, 1, 3, 2, 3. The right cosets of H are exactly the same as the left cosets, or H1 equals H1, 2, 3 equals H1, 3, 2 equals 1, 1, 2, 3, 1, 3, 2. H1, 2 equals H1, 3 equals H2, 3 equals 1, 2, 1, 3, 2, 3. It is not always the case that a left coset is the same as the right coset. Let K be a subgroup of S3 defined by the permutations 1, 1, 2. Then the left cosets of K are 1K equals 1, 2K, 1, 3K equals 1, 2, 3K, and 2, 3K equals 1, 3, 2K, which in set theoretic notation is 1, 1, 2, 1, 3, 1, 2, 3, and 2, 3, 1, 3, 2. However, the right cosets of H are K1 equals K1, 2 equals 1, 1, 2. But here, first, K1, 1, 3 equals K1, 3, 2 equals 1, 3, 1, 3, 2. Notice that we have 1, 3 in both of these, yes. But in the left coset we have 1, 2, 3, but in the right coset we have 1, 3, 2. And similarly, like an identical swap in the case of K2, 3, K1, 2, 3 equals 2, 3, 1, 2, 3. The following lemma is quite useful when dealing with cosets. We leave its proof as an exercise. Lemma 6.3. Let H be a subgroup of G, and suppose that G1 and G2 are in G. The following conditions are equivalent. First, G1H is equal to G2H. Second, H of G1 to the negative 1 equals H of G2 to the negative 1. Third, G1 of H is a subset of G2 of H. Like, this is just a very big thing. I'm just going to say this now. Because also notice that we can swap the G1 and G2 and then obtain that the cosets are actually the exact same, that they contain each other. 4. G2 is in G1H. And 5. G1 to the negative 1 G2 is in H. In all of our examples, the cosets of a subgroup H partition the larger group G. The following theorem proclaims that this will always be true. I'm just going to take a second to stress that this is going to be important as to what follows, why Lagrange's theorem works. So theorem 6.4. Let H be a subgroup of G. Then the left cosets of H and G partition G. That is, the group G is the disjoint union of the left cosets of H and G. Proof. Let G1H and G2H be two cosets of H and G. we must show that either G1H cap G2 of H is equal to the empty set, or G1H equals G2H. Suppose that G1H cap G2H is not equal to the empty set, and A is in G1H G2H. Then by the definition of a left coset, A equals G1H1 equals G2H2 for some elements H1 and H2 and H. Hence, G1 equals, actually I'll write this full line of logic because it's going to be A equals G1 H1 equals G2 H2. So then for elements H1, yeah, H2, so I'll know that H1 H2 is an H, which implies that G1, actually wait, a better way of writing it is that not AH2, G2 to the negative 1, G1 H1 equals H2. Or you can do it on the other side, G1 is equal to G2, H2, H1, negative 1, or G1 is in G2H. So in this case, we would write G1 is equal to G2, H2, H1 to the negative 1 is equal to G2, H2, H1 to the negative 1 is in G2H. Now, by lemma 6.3, that G2 is in G1 of H, we have that G1 of H is equal to G2 of H. Reminder that this lemma will specifically, just because of already the importance it has, will be proved to get a better idea of these cosets and operations we have on them. The whole exercise will be proved. Just saying that to hold myself to that later. Remark 6.5. There is nothing special in this theorem about left cosets. Right cosets also partition G. The proof of this fact is exactly the same as the proof for left cosets, except that all group multiplications are done on the opposite side of H. Let G be a group and H be a subgroup of G. We define the index of H and G to be the number of left cosets of H and G. We will denote the index by G colon H. Or, yeah, the index of H and G. So example 6.6. Let G equal Z sum 6 and H equals 0, 3. Then the index of H and G is equal to 3. One way to see that is to go back up. And we see that we have 3 cosets right here. Suppose that G equals S3 and then H equals the previous groups defined earlier. Then G, the index of H and G is 2 and the index of K in G is 3. Theorem 6.8. Let H be a subgroup of G. The number of left cosets in H is the same as the number of right cosets in H. Alright, this is the last technical proof before we get to the very cool stuff with Lagrange's theorem. So proof. Let L sub H and R sub H denote the set of left and right cosets of H and G respectively. If we can define a bijective map phi from LH to RH, then the theorem will be proved. So a reminder also, because it doesn't really draw attention to it, bijective is equivalent to 1, 2, 1, and onto. Alright, if GH is in LH, let phi of GH equals H G to the negative 1. By lemma 6.3, the map phi is well defined. That is, if G1H is equal to G2 of H, then H of G to the negative 1 equals H of G to the negative 2, or G2 to the negative 1, which is this lemma right here. To show that phi is a 1-to-1, suppose that H G1 negative 1 is equal to phi G1 of H is equal to phi of G2 of H is equal to H G2 to the negative 1. Again, by lemma 6.3, g1h is equal to g2 of h, which is by lemma 6.3 the equivalence. The map phi is onto, since phi of g to the negative 1h is equal to hg. So here we go. Here is the big stuff. 6.2, Lagrange's theorem. Proposition 6.9. Let H be a subgroup of G with G and G, and define a map phi from H to G of H by phi of H equals G of H. The map phi is bijective. Hence, the number of elements in H is the same as the number of elements in GH. Also, if you've noticed, this seems very much permutation-ish, because we have literally defined this under another name. You're having a right thought if you're thinking that. Proof. We first show that the map phi is 1 to 1. Suppose that phi of h1 is equal to phi of h2 for elements h1, h2, and h. We must show that h1 equals h2, but phi of h1 equals gh1 and phi of h2 equals gh2. So gh1 equals gh2, and by left cancellation, h1 is equal to h2. To show that phi is onto is easy. By definition, every element of GH is of the form GH for some h and h, and phi of h equals g of h. This is the central proof. Theorem 6.10. Let G be a finite group, and let H be a subgroup of G. Then, the order of G divided by the order of H is equal to the index of H and G, the number of distinct left cosets H and G. In particular, the number of elements in H must divide the elements in G. And this is because order of G over order of H is equal to the index of H and G, which is equivalent to the statement that G is equal to H, the order of H, times the cosets. Proof. The group G is partitioned into H, index of H and G, distinct left cosets. Each left coset has H elements. Therefore, by a simple combinatorial argument, the order of G equals the index of H and G times the order of H. Corollary 6.11. Suppose that G is a finite group and G is in G. Then the order of G must divide the number of elements in G. This is very quickly stated, but I will show why. So basically, the order of G, going back to cyclic groups, is actually the order of the cyclic group generated by G, which is a subgroup of G, which implies that the order of G over the order of G is equal to the order of G over the cyclic group generated, the order of the cyclic group generated by G is equal to this index, G index order of G, which is an integer, which is equivalent to saying in this case that the order of G divides the order of the group. Corollary 6.12. Let the order of G equals P with P a prime number. Then G is cyclic, and any G in G such that G is not equal to E is a generator. Proof. Let G be in G such that the G is not equal to E Then by corollary 6.11, the order of G must divide the order of the group. Since the order of the cyclic group is greater than 1, it must be P, because there are no prime numbers below it that divide a prime above it. Hence, G generates G. Corollary 6.12 suggests that groups of prime order must somehow look like Z sub P. Corollary 6.13. Let H and K be subgroups of a finite group G, such that G is a subgroup of H is a subset of K. In which case also H will be a subgroup of G and K will be a subgroup of H. Then the index of K in G is the same as the index of H in G times the index of K in H. Proof. observe that the index of g and k is equal to the order of g over the order of k is equal to the order of g over the order of h times the order of h over the order of k is equal to the index of h and g times the index of h and k. Remark 6.14. The converse of Lagrange's theorem is false. Note this is very important. We said that a subgroup must satisfy this. However, just because it satisfies that the order of a set or the order of a group is divisible by some number doesn't mean there necessarily exists a subgroup with that, unless you're given certain cases, but we're not going to get over to that. That's more so a silo theorem argument, but we'll get to that when we cross. We'll cross that bridge when we get there. The group A sub 4 has order 12. However, it can be shown tediously that it does not possess a subgroup of order 6. According to Lagrange's theorem, subgroups of a group of order 12 can have orders of either 1, 2, 3, 4, or 6. However, we are not guaranteed that subgroups of every possible order exist. To prove that A sub 4 has no subgroup of order 6, we will assume that it does have such a subgroup H, and show that a contradiction must occur. Since A4 contains 8 3 cycles, we know that H must contain a 3 cycle. We will show that if H contains 1 3 cycle, then it must contain more than 6 elements. Oh, this is really a brutal question to put as an exercise. Proposition 6.15. The groups A sub 4 has no subgroup of order 6. Proof. Since A sub 4, the index of H and A sub 4 is equal to 2, there are only 2 cosets of H and A4. Inasmuch as one of the cosets is H himself, right and left cosets must coincide. Therefore, GH equals HG, or GHG to the negative 1 equals H, for every G in A4. Since there are 8 3 cycles in A4, at least 1 3 cycle must be in H. Without loss of generality, assume that 1 2 3 is in H. If it's not 1 2 3, we can relabel the elements to be 1 2 3. Then 1 2 3 to the negative 1 equals 1 3 2 must also be in H. Since GHG to the negative 1 is in H for all G in A4 and all H in H, and 1 2 4 1 2 3 1 2 4 inverse equals 1 2 4 1 2 3 1 4 2 equals 2 4 3, and 2 4 3 1 2 3 2 4 3 to the negative 1 equals 2 4 3 1 2 3 2 3 4 equals 1 4 2. We can conclude that H must have at least 7 elements. 1 1 2 3 1 3 2 2 4 3 2 4 3 to the negative 1 1 4 2 and 1 4 2 to the negative 1. Therefore, A4 has no subgroup of order 6. In fact, we can say more when 2 cycles have the same length. Theorem 6.16. 2 cycles tau and mu in S sub n have the same length if and only if there exists a sigma in Sn such that mu is equal to sigma tau sigma to the negative 1. Proof. Suppose that tau is equal to a1, a2 up to ak, and mu is equal to b1, b2 up to bk. Define sigma to be the permutation, sigma a1 equals b1, sigma a2 equals b2, all the way to sigma of ak equals bk. Then mu equals sigma tau sigma to the negative 1. We will take this as given for now. Because this will send ak. This will send bk to ak. Then this will send ak to a1. Then this will send a1 to b1, as bk would be sent to b1 regularly. And likewise with that for everything. Conversely, suppose that tau is equal to a1, a2, up to ak as a k cycle, and sigma is an S sub n. If sigma ai equals b, and sigma of ai mod k plus 1 is equal to b prime, then mu of b equals b prime. Hence, mu equals sigma a1, sigma a2, all the way to sigma ak. Since sigma is 1 to 1 and onto, mu is a cycle of the same length as tau. Alright. A second to breathe, because this is a fair amount. For Ma's and Euler's theorems, the Euler phi function is the map phi from the natural numbers to the natural numbers, defined by phi of n equals 1 for n equals 1, n for n is greater than 1. Phi of n is the number of positive integers m, with 1 less than or equal to m less than n, and the greatest common divisor of m and n is equal to 1. So it's the number of co-prime digits from 1 up to n minus 1. From proposition 3.4, we know that the order of u of n, the group of units in Zn, is phi of n. For example, u of 12 has order phi of 12 equals 4, since the numbers that are relatively prime to 12 are 1, 5, 7, and 11. For any prime p, phi of p is equal to p minus 1. We state these results in the following theorem. Theorem 6.17. Let u of n be the group of units in Z and sub n. Then the order of u of n is equal to phi of n. The following theorem is an important result in number theory, due to Leonhard Euler. Theorem 6.18. Euler's theorem. Let a and n be integers such that n is greater than 0, and the greatest common divisor of a and n is equal to 1. Then, a to the phi of n is congruent to 1 mod n. Proof. Oh, this looks like a nice proof. By theorem 6.17, the order of u of n is phi of n. Consequently, a to the phi of n is equal to 1 for all a and u of n, or a to the phi of n minus 1 is divisible by n. Therefore, a to the phi of n is congruent to 1 mod n. This statement is just simply what it means for the greatest common divisor to be equal to 1 for them, and for it to be congruent to 1 mod something. So, if we consider the special case of the special case of Euler's theorem, in which n equals p is prime, and recall that phi of p equals p minus 1, we obtain the following result, due to Pierre de Fermat. Theorem 6.19. Fermat's little theorem. Let p be any prime number, and suppose that p does not divide a. Then, a to the p minus 1 is congruent to 1 mod p. Furthermore, for any integer b, b to the p is congruent to b mod p. We don't need to worry about stage. So Joseph Louis Lagrange, born in 1736, died in 1813, was born in Turin, Italy, and was of French and Italian descent. His talent for mathematics became apparent at an early age. Leonhard Euler recognized Lagrange's ability when Lagrange, who was only 19, communicated to Euler some work that he had done in the calculus of variations. That year, he was also named a professor at the Royal Artillery School in Turin. At the age of 23, he joined the Berlin Academy. Frederick the Great had written to Lagrange proclaiming that he was the greatest king in Europe, or proclaiming that the greatest king in Europe should have the greatest mathematician in Europe at his court. For 20 years, Lagrange held the position vacated by his mentor, Euler. His works include contributions to number theory, group theory, physics and mechanics, the calculus of variations, the theory of equations, and differential equations. Along with Laplace and Lavoisier, Lagrange was one of the people responsible for designing the metric system. During his life, Lagrange profoundly influenced the development of mathematics, leaving much to the next generation of mathematicians in the form of examples and new problems to be solved. So, state Lagrange's theorem in your own words. Lagrange's theorem says that, formally, it says there's two ways of formalization. First, super formally, super abstractly, the order of a G divided by the order of any subgroup H is the index of H and G. But more importantly, it's that the order of subgroup H divides the order of G. Determine the left coset of 3 in Z sub 9. So for this, we have the set 0, 3, and 6. And we know that each coset is going to have the same number of elements. So we're going to have 1, 4, 7, and 2, 5, 8. And if you're thinking very weirdly, you can kind of think of a way we add 1 to all these to get this, we add 1 to all these to get this, we add 1 back to get all these. This kind of looks like a weird set theoretic way of doing addition modular 3. And later on when we learn quotient groups, we're going to see that this intuition we will be able to say that the integers mod 3 are isomorphic with this quotient group. And this will actually be a very important example coming up. So the set 0, 1, 2, 3, subgroup S4, what is its index in S4? So this subgroup has order 1, 2, 3, 4. And S4 has order 4 factorial. So the index of S4, we'll call this group X, is equal to the order of S4 divided by the order of X is equal to 4 factorial over 4 is equal to 3 factorial is equal to 6. Alright, suppose that G is a group of order 29. Describe G. So, if G is a group of order 29, if I'm remembering correctly, 29 is a prime number, which means that since we take any element form its cyclic group, it's a finite subgroup, and this number is prime. That means that every number is a generator of this is a generator of our group G. And by the definition of what that means is that our group is cyclic. Our group is actually Z to the 29, or Z sub 29. Alright, 5. The number P equals 137,909 is prime. Explain how to compute 57 to the 137,909 mod 137,909 without a calculator. So we use Fermat's little theorem over here to get that B to the 137,909 mod 137,909 is congruent to B mod P. So this will actually just be congruent to 57 mod 137,909. Alright, we have, from the looks of it, short exercises, but very good exercises from what I remember. So I'm going to take a quick intermission to grab some coffee and chill. Alright, testing, 1, 2, 3. I had grabbed myself a large cup of coffee. Oh, that was horrible. Oh my god, that's gonna be in the recording, isn't it? Oh no. Alright. Is sound coming through? Oh no, oh god, I just heard the playback of that horrible pun in my ears. Okay, so we're gonna pretend that didn't happen. We're gonna get back to this. Alright, first, actually, I'm gonna just quick clear the whiteboard. So. Suppose that G is a finite group with an element G of order 5 and an element H of order 7. Why must the order of G be greater than or equal to 35? So, okay. Suppose that G is equal to 7. Actually, for this, just suppose that the order of G is equal to P and the order of H is equal to Q for P and Q primes. I mean, they could be co-prime. I think that'd make the theorem work, but like it's kind of complicated, so excuse me. So we have oh no, I'm burping like mad. So the order of G is equal to P, the order of H is equal to Q. Now, let's take the cyclic group G and the cyclic group H. We're going to show that no elements of these groups are in the same, like, basically the intersection of these groups is the trivial group. And the way to see that is like, suppose there was some other number, some other thing, like let's call it G prime. Then that means that G prime, the order of G prime is equal to P is equal to Q, because these are primes, but P is not equal to Q. So this is a contradiction. However, what this also means is that for every G, for every H in H, or every H in the cyclic group of H, we have that the order of G H is not equal to the order of G H prime if H is not equal to H prime. One way to see it is that these sets are disjoint, and that if you multiply it by H in this, you have H in one of your cosets, and if you multiply it by H prime, you have H prime in the other one of your cosets. And we'll prove later on that these are only equal if they both have the same elements, and obviously they can't, like this group can't have H prime, this group can't have H, so they must be disjoint entirely. And there are at least the order of H of such disjoint cosets of G, which means that the order of G is less than or equal to the order of G, and all the possible cosets of G, which is actually the order of H, which is equal to PQ. In the example given for 1, we have that 5 and 7 are prime, so 5 times 7 equals 35, so G is greater than or equal to 35. There we go, clear the board. Suppose that G is a finite group with 60 elements. What are the possible subgroups of G? So 60 factors into 2 times 2 times 3 times 5? Let me grab a calculator and double check. Wait, let me do math. 4, 12, 60. Yeah, okay. So we have either a subgroup of order 2, or when there are 2 of them, so like we just know that the subgroup will be of order 2, we're only worrying about the orders of the subgroup. A subgroup of order 3, a subgroup of order 2 times 3, a subgroup of 2 times 2 times 3, a subgroup of 5, a subgroup of 5 times 3, a subgroup of 5 times 2, or a subgroup of 5 times 3 times 2, or 5 times 2 times 2. Basically, any reduction in the sense of removing one of these like prime factors will give us a new possible order of a subgroup of G, or a subgroup of 60, or a subgroup of G if G is the order of 60. So, prove or disprove. Every subgroup of the integer has every subgroup of the integers has finite index. So, first of all, what it's going to be is that it's showing that Lagrange's theorem is going to be false for infinite sets. So let's actually, I looked ahead for a second. This is obviously false, because every subgroup of the integers minus a 0 subgroup, like 2z is a subgroup, is also an infinite subgroup. But let's actually show that it has finite index. So suppose, first of all, we know that all subgroups of the integers are going to be of the form nz for the integer nn. Yeah, that will be right. So it'll be nz for, ironically, n in z is going to be a subgroup. So the index of z, n of z, well, we can think about it by where the representative 0 is sent to. So we have the element, the first subgroup being like negative n, 0, 1, or yeah, negative n, blah blah, n, blah blah blah. Then we have, we'll call this the 0th group, you'll see why I'm calling it this. This is equal to the one group is going to be negative n plus 1, 1, n plus 1, 1 and on. And we're going to go all the way up to the n minus 1 group, which is equal to negative 1, n minus 1, n plus 1. It's just we're going to have 2. Well, negative n plus 1, n plus 1, so we're going to have 2. 2 and minus 1 still, yeah. What am I thinking? Oh yeah, I'm very dumb, yeah. Because we already counted for that case. 2 and minus 1. And then afterwards, if we actually try to add 1 to this, we try to add n, well, we're actually going to cycle back to this group. And I'm being very deliberate when I say we're going to cycle back there. This coset structure is actually, we have n cosets in ed_z. And we might also notice that z sub n has n elements. And we might notice that their representatives look like a lot from these cosets. This is all interrelated. When we get to quotient groups, it will all come together in a beautiful display of glory. But know that this structure, this coset structure, is going to be integral in order for understanding the integers mod n. But ultimately, to answer the question, there are n cosets. Okay, so also notice as well, we proved that every subgroup of the integers has finite index, but we did not prove that it has finite order. So, okay, 5. This is the left and right coset subgroup. Okay. I'm lazy. Yeah, I mean, these are kind of boring, but this is actually interesting. So T is a circle group. So T is a set of all complex numbers such that the absolute value of z, actually I should write T is a set z in C star. We don't need to define C star explicitly, but for the sake of making it a subgroup, it's nice, such that the absolute value of z is equal to 1. I'm also doing this example because it's an example of an infinite group, which I both have less experience with and also acts way funkier. And we'll show how it acts way funkier. So, what are the cosets of this? The coset of this will be, for example, suppose we have C T1. Well, it's going to be, first of all, we know that we'll have order, we'll have C T1 equals C T1 is equal to C. So we can plot this in polar coordinates. So we can write this as R cis theta. And then we can call this cis theta prime. Notice here that because we know the order is the norm is 1, that we can already assume that R is going to be equal to 1. So from here, to determine like the properties, the actual, let me think about how I want to phrase this, because here's like a really specific idea I'm going for. To talk about in a good way the cosets. Suppose as well that we had like C T2. Or no, what do I want to do? Yeah, okay. Basically, suppose the order, here's what I'm going to do. Suppose that the order of C prime is equal to the order of C. So we have that C prime is equal to R cis of theta prime prime. And we want to basically show that, then the element C over C prime, the order of this is going to be equal to, the order of this is going to be equal to 1, which implies that C over C prime is in T, which implies that C prime C over C prime is in C T. And the fundamental fact here is that all we cared about, the only restriction, and the restriction that actually matters to make this work, is that the radiuses are. So if the order of C is equal to R, C T is equal to the set of all Z in C star, such that the order of Z is equal to R. Describe the left cosets of SL2R and GL2R. What is the index of SL2R? GL2R. Nah. Most likely, I'm assuming it's going to be something where it's like, it'll be something similar to this with the invariant, where it will be the coset, basically if GL2R, if the matrix has determinant R, SL2R, the coset of that, will be the set of matrices with determinant R instead of determinant 1. Because generally it seems like restricting anything to a matrix, restricting anything that can be to a matrix with an invariant, the cosets describe things for that invariant is changed to what you're taking the coset of. Verify Euler's theorem for n equals 15 and n equals 4. No. Use Fermat's little theorem to show that if p equals 4n plus 3 is prime, then there is no solution. Oh, this is actually kind of big. Then there is no solution to the equation x squared is equal to negative 1 mod p. Alright, so. Oh, this is funky. So Lagrange's theorem, let me actually go back to read instead of just like, oh, it used Lagrange's theorem, did it say? Oh, Fermat's little theorem. Yes, okay. A to the p minus 1 is congruent to 1 mod p. B to the p is equal to b mod p. So what this is saying also, first of all, let's notice that x squared is congruent to minus 1 mod p is the same thing as saying x squared is congruent to p minus 1 mod p. Which is 4n plus 3 is prime. And there's no solution, so 4n plus 3. So like we have mod 4n plus 3, so we'll x squared 4n plus 3 mod p minus 1 mod p. So x squared is equal to 2n plus, or no, 4n plus 2 mod p of x squared is equal to 2 n plus 1 mod p. So like, let's think a little bit more literally about what this means. This means that x squared is equal x squared minus 2 n minus 2n plus 1 minus 4n minus 2 is equal to c 4n plus 3. So we get that x squared is equal to c4n 4n c minus 1. Okay, actually this is like way too complicated a method. I don't want to deal with this. So let's think. So Fermat's little theorem, P does not divide A. So x squared P minus 1 mod P Oh gosh, I'm getting confused at this. Okay. X squared minus 1 mod P. X squared plus 1 is congruent to P mod P. Wait, I'm confused. Okay. So from here, which is just the same as saying x squared plus 1 is equal to 0 mod P. Alright, why is this impossible? Oh gosh, okay. I mean, it's gonna be something about the fact that it's 4n minus 3. It's the thing I don't get. 4n plus 3. So 4n plus 2 mod P. Where is this? So wait, we subtract and we get that x squared minus 1 is congruent to 4n mod p. And then we get that x plus 1, x minus 1 is congruent to 4n. Wait, am I doing this right? Okay, let me double check. I'm genuinely like really unsure. Wait, okay. Used for Maslow's theorem, plus 3 is prime. Plus 3 gets you minus 1. So x squared minus 1, which you can factor as x plus 1 as an x minus 1. Which this implies, because this is 2 squared. Alright, so the only way for this to be valid is if this right here. Wait, no, okay, I can't treat this like a regular equation necessarily. So x plus 1, x minus 1 is congruent to p cp minus 4n. So x plus 1, I don't think this is how they intended to do it, but I'm going to try, just expand this, see what I get. C of 4n plus c of 3 minus 4n, which gets us x plus 1, x minus 1 is equal to 4n c minus 1 plus c3. I should also see. What does this tell us? Doesn't really tell us anything. Okay, let's go back to the drawing board. So x squared. So we're assuming that x squared is congruent to what mod p? It's congruent to, let's call it blank for now. No, x squared is equal to 4n plus 3, all multiplied by c, plus some number k. We're trying to figure out what that k is. No, okay. Let's think. Alright, let's just do a normal proof by contradicting, because it wants us to show that there's no solution. So we suppose there is a solution. Let's suppose that x squared equals p minus 1. Which is the same thing as saying negative 1. So, for Maud's little theorem, let P be any prime number and suppose that P does not divide A. Then A to the P minus 1 is congruent to 1 mod P. For any H for B, B to the P is congruent to B mod P. Alright, what if P does not divide A? What? Oh gosh, okay, 1 is 4n plus 3. So 4n plus 3 equals P squared plus Q squared. What does it say about P and Q? Oh god, I don't know. I mean, we can use Fermat's little theorem to say that x squared is congruent to x mod 2. Not really saying much. Should be B to the P is equal to P mod P. I'm just wondering where the representation that, like, because the only next step I can take, is that P is equal to 4n plus 3. To get that x squared is congruent to 4n minus or plus 2 mod P. I could just then do x squared is congruent to 2 times 2n plus 1 mod P. There's not much I can do with that though. P's not divide A. I mean, I guess. Okay, here's a really random idea. So, x, like, choose a representative x less than P. And we can always, P plus 1 we can actually say. We can always choose a representative x less than P. which means that we can apply Fermat's little theorem to get that x to the p minus 1 is congruent to 1 mod p. Applying the definition of x gets us 4n plus 3 is congruent to 1 mod p. Is that x to the minus 1, x to the 4n plus 2 is congruent to 1 mod p. X to the squared 2n plus 1 is congruent to 1 mod p. Which is that x squared to the 2n plus 1 is congruent to 1 mod p. Which somehow we have this information, and this means that x squared is congruent to 1. Alright, so how do we solve this? I mean, this is nearly right. It's like, okay. Suppose that x squared now is congruent to negative 1, right? Then x squared to the 2n plus 1. The nice thing is that 2n plus 1 is always going to be, it's going to be odd, is going to be congruent to, it's going to be congruent to negative 1 to the 2n plus 1. My heart rate is beating. Is congruent to negative 1 to the 2n. Negative 1 is congruent to negative 1, which is not congruent to 1. Contradiction. Oh my gosh, that problem was a lot. That seems like the right work though. Oh man, okay. Can't say that I don't work for these problems sometimes. So, okay. Okay, show that the integers have infinite index in the additive group of rational numbers. I'm too lazy for that. This is going to be a similar idea. But basically show that the indexes, we can make them arbitrarily fine with like 1 over 2 to the I. Let h be sub, okay. Also, I'm gonna run to the restroom. So actually, I will keep this on in case you want to have a good look at the problems while I take a short. Can I like add text onto this? Text. Oh no. Oh, OBS, please spare me. Oh my god, okay. Oh no, okay. So checks running to the rest of the problems. Alright, and we are back. And while I was having myself a think in the restroom, I will go back here. Actually, I'll go to the working board this time. And I'm going to show why the argument for the previous question only works in the case of 4n plus 3. So if we have 4n plus 1, right? What we're going to have is that we'll be able to choose a representative x such that 4n plus 1 minus 1 is congruent to 1 mod p. This is going to be x to the 4n is congruent to 1. But realize in this case, x equals 1, x equals negative 1 is still valid for this. Or like x squared equals 1, x squared equals negative 1 is still valid for this, because this is the same as saying that x squared to the 2n is congruent to 1. When it's 2n plus 1, as it was for the previous case, then it works. But in this case, since we just have 2n, we don't have enough information to tell us yet. Alright, so going back to the standard textbook scene. Alright, check goes infinite index in the additive group of complex numbers. Yeah, so, oh gosh, okay. I hope I didn't mess anything up on OBS, so. These are fundamentally the same thing, basically showing shifts in our groups. Let H be a subgroup of G, and suppose that G1 and G2 and H. Prove that the following conditions are equivalent. So we will prove, hopefully, we'll prove a chain of equivalences like so. So, okay, A implies B. So suppose G1H equals G2H. This means that for any G1H1, we have that there is a G2H2. Now, what we do is that we multiply this by G1H is equal to G2H. Wait, let me think about how to best phrase this. Alright, so we can multiply both of these by G1, -1, G1, H1, G1, -1 is equal to, actually wait, no, that's kind of a horrible way of phrasing it. So suppose that we have H of G1. Suppose we have H of G1 in HG1. Then we know that by previous coset definitions that, okay, let me think about it in advance for a second. So we're ultimately going to be looking for an element H prime. Actually, let's think HG. Instead of HG1, we're not going to work with that. We're going to work with better notation. So we're going to have HG in HG. And ultimately, we're going to be looking for some H prime G prime, which with H prime G prime equal to HG. So to isolate G prime, we multiply on both sides. G prime equals H prime H of G. Then we multiply on the left by G inverse. So G inverse of -1 is equal to E is equal to G prime inverse H prime H of G. Then we multiply on the right side to get that G is equal to G prime to the -1 H prime H. Now we multiply on the left side to get that G H -1 is equal to G prime to the -1 of H. Yeah, so what this would show us is that if we have, okay, so what we're trying to show is that HG1 is, yeah, I think, wait, okay, my brain is getting confused. Oh gosh, we're talking about the inverses, and we have all these inverses going everywhere, and that's ugly. To the -1, so replace the G primes -1. So basically, suppose we have HG in HG, and we want to show, and we also have that GH equals G prime of H. This is the same as saying that G to the -1 G of H, or G prime to the -1 G prime of H, G of H, or G -1 is equal to H. Just the same as saying that. So ultimately we're looking for H and G prime, such that we know this. Then we're looking for G and gosh, my brain is exploding. Okay. So GH equals G prime H, G to the negative 1, G of H is equal to H. So what we could do I'm wondering nah. Okay, let's think more clearly about this. Brain. So okay. Suppose that we have GH. Actually, you know what? Screw it. I want to use these characters. Suppose we have XH is equal to YH. Now suppose that we have H x to the negative 1. We want to show here that it is equal. Let's work in reverse. So we want to show that it's equal ultimately to some H prime y to the negative 1. So we want to discover what that y to the negative 1 is. So first we multiply by xh to the negative 1, y to the negative 1. And we want to show that this is in H prime. We want to show that this is in H, because if this is in H, then that would imply that setting H prime equal to this will give us an element equal. So, in order to show this, we first, since we have x is equal to xy, we have that x h is equal to y h prime, right? Or h, for the sake of argument, we're going to call this h prime h double prime. So we have that. Gosh, let me think. First of all, we have that x is equal to y h prime h to the negative 1, h prime to the negative 1. We know this is all in h. Wait, okay, I'm thinking. We could be a bit clever about this. Let's be a bit sneaky. If it works, okay. So is x h equal to x prime of h? Or no, x to the negative 1 of h. Not necessarily, no. Wait, what am I? No, I'm dumb. What you want to show is that hx to negative 1y is an h. So we have okay, let's think carefully about this. So if the statement is equal, if h of x to negative 1 is equal to h to the y of negative 1, we have that h of x to negative 1 is equal to h prime y to the negative 1. And solving, we multiply on the right by both sides on the right by y to get h to the negative 1, y is an h. Right. So we have that here. We have that to get this. So first, from here, we have xh is equal to yh. We have x, h prime to the negative 1 is equal to y. Note this is still an h, which means that h prime to the negative 1 is equal to x to the negative 1 y. Oh my god, okay. H to the negative 1 equals y, so then letting h to the negative 1 be that. Instead, we get that h prime to the negative 1 equals h, and since the inverse is that, we have what we want. Okay. Okay, let me go over that argument again. Except in not as much like detail of I'm obviously sweating. So, suppose that xh is equal to yh, and suppose we have hx. Now, h to the negative 1, x, we know by assumption that x, h to the negative 1, is equal to y, h prime, right? So we have that, yeah, we have x, we have this term hx to the negative 1. So we have x, h to the negative 1 is equal to y, h prime. We multiply on the right by h prime to get h to x, h to the negative 1, h prime to the negative 1 is equal to y. We multiply on the left to get h to the negative 1, h prime to the negative 1 equals x to the negative 1y. And we get, multiplying on the left, that h prime to the negative 1 is equal to h x to the negative 1y. Which means that this is equal to, which implies as well that, which implies that h prime to the negative 1, y to the negative 1 is equal to xh to the negative 1, which means that is hx to the negative 1 equals h prime to the negative 1, y to the negative 1. And note here that this is in h. And that completes the proof of A to B. So this was all of equivalent, showing that A implies B. And actually, a very similar argument will show you B implies A in this case. So we'll just take as given for the sake of time right now that A and B are logically equivalent. So, now, h to the negative 1. So obviously, if these are equal, we're going to, like, for A implies C, we have simply that literally A implies C, right? that equality implies inclusion. Now, suppose that G1 H is equal to G2 H prime. Then this means that G1 of H prime inverse is equal to G2. This is in H, so we have that G2 is in G1 H. So that's C implies D. C implies D. Then D implies E is at G2. So we say that if G2 is equal to G1H, so G1H, we want to show that G minus 1, G2, oh yeah, G1 minus 1, G2 is equal to H in H, right? That shows that. That shows the equality D to E, or the implication D to E. And now the coup de grace. So suppose that G1 minus 1, G2 is equal to H. And now suppose as well that we have H prime of G1. This means that G1 H prime to the negative 1 G2 gives us H prime to the negative 1 G1 to the negative 1 G2 is equal to H, which is that H prime negative 1 G1 to the negative 1 is equal to H G2 to the negative 1. And in a similar case, H prime G2, we multiply on the left by G1, and we get that E implies A implies B, or implies either A or B, but we know that A and B are equivalent, so if it implies A, then it implies B, and if it implies B, it implies A. Which shows all these strings of equalities. GG is an H for all G and G, and H is an H. Show that right cosets are identical to left cosets. For this, you literally just like multiply the G on the right. It fails in the proof of Theorem 6.8 if phi of R, if phi of LH to RH is defined by phi of GH equals HG. This is that, okay, Theorem 6.8. Let's see how the actual theorem goes. Let H be the number of left cosets and G assumes if we can define a bijective map, basically, we don't necessarily have a well-defined mapping. Actually, yeah, so we have this is insured. We don't have that. We can just commute the terms and get another like well-defined map. Oh no. Internet, no. Okay. Suppose G equals H if the order of G divides N. If the order of G, if G to the N equals E, the order of G divides n, which implies that. Oh wait, actually, I thought we were trying to be able to prove. Show the order of G divides. Oh, okay. Oh, it's just another Lagrange's theorem argument. Okay, we can don't worry about that. Okay. The cycle structure of, for example, if you is defined as the unordered list of the sizes of the cycles. So 2, 3, 4, 2, 3, 2, 1. Let's 1, 2, 2. Things for any permutations of cycle structure if and only if there exists a permutation of gamma. Ah, gosh. This is important, but no. This looks painful. Okay, if G equals 2, prove the element. No, prove that the number of elements of order 2 is odd. Use this result to show that G must contain a subgroup of order 2. This is asked earlier on. Okay, prove that the number of elements of order 2 is odd. I mean, oh, because the identity has order 1. Okay. Oh yeah, since the identity is order 1 and the elements of order 2. Okay, for this, alright, so let delta prime of G equal to set of all G in G such that oh yeah. So basically like alright, if G is equal to 2n, prove that the number of elements of order 2 is odd. Prove that the number of elements of order 2 is odd. Oh yeah, so basically if you have 2 elements of order 2, then they by definition, any odd amount of yeah, so if you have m elements of order 2, then for example, since they are of order 2, let's call them 1, 2, 1, 3. We have 1, 2, 3, on and on. We have entries 1. We have m total elements, and we can choose m, choose k of them. That or it's too. I'm trying to think. There's a way of nicely phrasing it using like Lagrange's theorem. So like suppose we have elements G1 up to Gn of order 2, right? Oh gosh, I don't know how to define things properly. Have this work nicely. If the order of G equals 2n, prove that the number of elements of order 2 is odd. I mean, is it going to be an induction type thing? Where it's like, okay. So suppose that our group G, first of all, okay, the case is trivial when we have G equals 2, right? Because then it's just like congruent to the integers modulo 2, which obviously is an element of order 2. So suppose we have a group 2n, and suppose E is not equal to G is in G. Then we have the order of G is either equal to 2 okay, so let's think. So if we have an even number of elements of even order, I'm trying to think. Oh shoot, it's kind of hard. This is hard to just like conceptually wrap my head around. It may or may not be too late for this. Okay. I don't want to put it off. I don't. Okay. Okay. I may come back around to it end of stream. But for now, okay. Suppose that G, with H, is equal to 2. If A and B are not in H, show that AB is in H. So suppose. Alright, so if A and B are not in H, that implies that, excuse me, if A and B are not in H, that implies that AH is equal to BH. H, B is an H. So A of H is then equal to AB of H. If A of H, so what we then show is that A of H is equal to H. So suppose AA is not equal to H. So if AAH is not equal to H, AH is not equal to H, implies that H cap AH H implies that AAH cap AH is equal to the empty set, which implies that the index of GH is greater than 2. Yeah, it's easy to show that a squared cannot be in. Oh, and how we're defining it, it's easy to show that a squared cannot be in H, or a squared cannot be in AH. So if we assume it to be different, then it implies that it's greater than 2. Okay. HK p sub root 2 for the GH cap GK is a coset of H cap K in G. I mean, this is fairly simple. Because if it's in both GH and GK, so like if it's equal to GH1, GK1, then H1 equals K1, which means H1, K1 are in H cap K. So if GH equals 2, prove that GH equals HG. Well, because if not, then you would have, first of all, if it's H, it's trivial. If it's not, then you would have at least 3. Which actually, by the way, this is a very important theorem, but oh well. I've never seen double cosets used in the rest of the book, so I'm not going to worry about that. Let G be a cyclic group of order n. This is exactly the statement that every the amount of greatest common divisors, the amount of n such that GCD of n, GCD of m and n is a generator. If they're prime, let n equal p1 a1. Just prove that fe of n equals 1 minus p1, 1 minus p2, all the way up to 1 minus pk. So first of all, for this, for 22, so we'll have the case first. We'll prove induction, or we'll prove for the first one, and then we'll prove it for if you have n primes concatenated together. Multiplying them by another prime completes the theorem. So, for example, if n is equal to p1, first of all, if n is equal to p1, then p1, then phi of p, yeah, okay, so if phi is equal to p, if n is equal to p for a problem p, phi of p equals p minus 1 equals P1 minus 1 over P. Then if n is equal to P epsilon, V of okay, first of all, V of P times Q. Yeah, I think C is Q. Okay, I'm not gonna worry about. I'm pretty sure it's a multiplicative function, but I forget. V of P. Is equal to P epsilon minus epsilon, right? Because, for example, at P squared minus, like, besides P and P squared, you have nothing. Oh, actually, is that true? First of all, let's kind of like cheat in advance. Epsilon minus 1. So, are there exactly... P. Yeah, this seems right, roughly. Why though? So there are P epsilon 1. So like, okay, so for P epsilon, you have P, you have P times 2, all the way up to P times P is equal to P squared. How many are there? There's P, 1, 2, there's P of these. Oh, and it will be P epsilon minus 1. So it's actually P epsilon 1 minus 1 over P. Sick. Okay. And then the rest actually follows from the fact that I won't prove it here, that phi is what we call a multiplicative function. You multiply the two functions, you multiply two inputs, and you multiply their outputs. That is something not particularly fun to prove, but it works. And it's actually proving it in a method similar to this. So, show that if n is equal to divisor of n for all positive integers n. I'm far too lazy to show that. Yeah, I think I've been streaming problems for like nearly an hour, because the reading did not take that long. So I think for the sake of getting some sleep, we have Introduction to Cryptography. I think we have Introduction to Cryptography, followed immediately by, oh gosh, this book is working as intended. Oh, that works. That works as like a, alright, Introduction to Cryptography and problem Algebraic Coding Theory. Okay, Algebraic Coding Theory is huge, especially for this book. This book commonly will not spend 20 pages, over 20 pages actually, on a subject. So I don't know if I'm going to do both Algebraic Coding Theory and Introduction to Cryptography, but they would be fitting together. So I might stream them both in the same day. For now though, I've done enough problems. God, I'm tired. Yeah. I guess yeah, I'll pretty much leave it at that for the stream. Thanks for tuning in. Have a nice